I have a few more pages of pointers to other topics written out here that I want to tell you about for a minute, and then I want to have a wrap-up session. So let me organize myself for a moment and get you those other things that I've had time to write out so far. And then the other ones that I wanted to tell you about, I'm going to be writing out some more notes and posting them on the webpage after the course is over. So someone asked about the Bayesian outlook on multiple comparisons. And so I was just teaching about this in the course I've been teaching at Santa Cruz. And so I can give you a pointer directly. Go to this particular website, which I will go to now, and you'll see a web page that looks something like this. And if you scroll down under the part called Lecture Notes and Extra Notes, and you scroll down to the day called 12 March, Lecture Notes Part 20, you'll get an idea of my sense of what is the right way to think about multiple comparisons. So the basic topic here is one-way fixed effects analysis of variance. This is a web page from the course that I'm teaching. I just finished teaching at Santa Cruz, and if you go down to the relevant part of it and click on the lecture notes, you will find the following. Multiple comparisons arises in a variety of contexts, and one of them is when you have a number more than two groups to compare with each other and you want to know how different the means are. That's a simple problem. People have been thinking about it since Fisher in the 1920s. And this simple version of it is called one-way fixed effects analysis of variance. That's what Fisher called it anyway. And so the basic off-the-shelf model is that you have real numbers yij, and I indexes which group the person comes from. You could think of as I runs from 1 to k, so you can think of there being k different treatments, or in any case, there's k groups of people whose means you want to compare, and j indexes the person inside that particular ith group. And the simple model says that each group has its own mean, theta I, and each person has their own random effect that's specific to that person, E sub ij. And the E sub ij's are regarded as IID draws from a normal distribution with mean 0. And in Fisher's original work, everybody has the same variance, sigma squared. And so right away, there are two things you might question. Why normality in the so-called error distribution? And even if you spot him normality, why do they all have to have the same variance? Why not sigma squared sub I, for example? So group I gets its own standard deviation. And the answer is not a very good one because it's just that Fisher couldn't develop the math. He could not work out an optimal frequentist procedure if he allowed population I to have its own standard deviation. Of course, that's easy enough to solve more generally in a Bayesian fashion today. It's not hard to do, but basically he had to start somewhere, and so this is where he started with the Gaussian and with equal variances. So you can work through the maximum likelihood estimates are just what you'd expect. The maximum likelihood estimate of the mean in group I is the sample mean in group I. Why not, right? And you can get a maximum likelihood estimate of the overall pooled variance, as it's called, and it involves this 1 over n thing, capital N thing here, where capital N is the total number of data values. And that's biased, and so you can show without much trouble that if you divide by n minus k instead of by n, you get an unbiased version. And then Fisher went on to develop an elaborate theory for testing the null hypothesis that all the population means were equal. And that's not all that interesting to me because all you get at the end of that is a single p-value, which, as I've said before, comes out on the wrong scale for understanding what's going on. So instead, let's start talking about comparing the thetas with each other in a pairwise fashion. So let's think of all the different possible pairwise comparisons, theta 1 minus theta 2, theta 1 minus theta 3, dot, 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 down to theta k minus 1 minus theta k. There are k choose 2 of them, which is k times k minus 1 over 2. And already we know how to compare two means because we've done it several times this course. So you can easily build a good confidence interval for the difference between two of the means, let's say theta I and theta I prime. So there's obviously the estimate, the point estimate is the difference in the means in those groups. And you can work out what the variance is. Under the pooled assumption, it becomes sigma squared times 1 over ni plus 1 over ni prime. And now you can go ahead and move toward constructing one of those t intervals that the frequentists are so fond of. And so the estimate minus the truth over the standard error of the estimate turns out to have a distribution that's independent of all the parameters. It's the t distribution with capital N minus k degrees of freedom. And so now the frequentist best confidence interval looks like that. You go yi dot minus yi prime dot is your estimate plus or minus the right t number times that standard error, which is the square root of the pooled variance estimate, sigma hat u times the square root of 1 over ni plus 1 over ni prime. All right, good. So now that we know how to do one of those comparisons of two means, you can readily compute all k choose 2 of these intervals as I and I prime run from 1 to k, with I not equal to I prime. And then you can readily conclude statistically significant differences by just looking to see which intervals fail to include 0. And this is all a perfectly good approximation to a full Bayes answer with diffuse priors. You might get a slightly better answer from the Bayesian story in terms of accuracy of what you're doing if the sample sizes are quite small. But in fact, because Fisher, building on the work of that guy Gossett, was able to come up with a function of the data and the parameters that had a distribution that was independent of the parameters and had an easily tabled form, namely that t distribution. Basically, that's what you're going to get from the Bayesian point of view as well with diffuse priors. Now, this procedure will have a particular false positive rate of saying things are significantly different when they're not, and it will have a particular false negative rate also. And Neyman would have called those type 1 and type 2 errors, Roman numeral 1 and 2, as we talked about before, where positive corresponds to announcing that a difference exists. Now, there are people who think in this problem that you should be worried only about the false positives. And in fact, you do have a reason, if you're a person who obsesses about false positives, you do have a reason to be worried, because actually what you just did was you made k choose 2 different pairwise comparisons. And if each one of them has a, let's say, 5% chance of being an interval that doesn't include the truth, then your overall chance of having one or more intervals that don't include the truth is probably quite a bit higher than 5%. So, all right, good. So the standard hypothesis testing position is to be terrified of false positives and to, quote, take care of the false negatives by having designed the experiment in such a way that you got enough data to make the false negatives unlikely, subject to a bound on the false positives. You remember that's how Neyman and Pearson set things up. That creates the so-called multiple comparisons problem. Looking only at false positives, if you build each of these k choose 2 pairwise intervals at the 95% level, clearly your overall chance of at least one false positive mistake is bigger than 5% and possibly substantially bigger. Many frequentist methods have been developed to address this problem, and some Bayesian methods also. False discovery rate, FDR, Bayesians are trying to work with this. The simplest method is based on what's called the Bonferroni inequality, which you may have heard before. And it basically says that for any sets A1 through AN, when you're back in Kolmogorov's world involving sets, the probability of the intersection of all those is greater than or equal to the sum of all the separate probabilities minus n minus 1, where n is how many different sets you're trying to intersect together. And this bound is in general not tight, and so Bonferroni tends to be conservative, but at least it provides you a way to bound your error rate. Because if you apply it to this problem here, you want to make little m confidence statements with overall simultaneous coverage 1 minus alpha. Let's let statement j be made at confidence level gamma j. Then Bonferroni says the probability that all little m of your statements are true is like one of those intersections I said, and that's the left-hand side is supposed to be 1 minus alpha. And that's greater than or equal to the sum of all the separate probabilities each statement is true minus little m minus 1. But that's the sum of the gamma j's. And so in the end, we can make it all work if we have the mean of the gamma j's be less than or equal to 1 minus alpha over m. And the simplest version of this idea is just to make all the gamma j's the same. And so now what happens is you should make each of those statements not at level 1 minus alpha, but at level 1 minus alpha over m. And the jargon that frequentists say is you've taken your alpha and you've decided to spend it across those comparisons. Let's see, this is the situation where there are m comparisons being made. you decide to spend it by giving each one of them alpha over m worth of error rate, and when you add that up, you get no more than alpha. So all possible pairwise comparisons in the one-way fixed effects ANOVA, m is k choose 2, and so you ought to build each t interval at level not 1 minus alpha, but 1 minus 2 alpha over k times k minus 1. So that's the Bonferroni story, and I'll give you a little numerical example quickly. Suppose that capital N is big enough that the t story is the same as the z, the standard normal story. Then all your pairwise comparisons will look like the difference of the means plus or minus a number from the normal distribution, that's that capital phi inverse thing, times the standard error. And if no multiple comparisons adjustment were made at all, that number would always be 1.96. So let's look and see what it rises to from Bonferroni as a function of how many groups there are. If there's only 2 groups being compared, obviously there isn't a multiple comparisons problem. And so the answer with no adjustment is the same as the answer with the Bonferroni adjustment, and the ratio of those 2 numbers from the z table is 1.0. When there are 3 groups to be compared, there are 3 choose 2 is 3 different pairwise comparisons, and the number from Bonferroni rises to 2.39, and the ratio is 1.22. And so already when we go from 2 groups to 3, each interval has to be 22% wider than it would have been if we were not adjusting for multiple comparisons. When we get up to 5 groups we're comparing, there's 10 possible pairwise comparisons. It rises to 2.81. Now each interval has to be 43% wider than if we didn't make such an adjustment. And when k is 10, there's 45 such groups, and we're all the way up to 3.26. And the ratio is now each interval has to be 66% wider to get the Bonferroni thing happening. Now I'd like to make a criticism of this point of view as follows. At analysis time, you will want to have the freedom to be able to balance false positive mistakes against false negative mistakes. And there are 2 reasons for that. You may have had no control over over capital N, the total sample size at design time. And or, item B, a value of capital N that adequately controls the false negative error rate for a procedure like Bonferroni, or even a better method, may simply be too expensive or too time consuming to achieve. And so the standard frequentist thing, which scolds you and says, oh, you should have thought of this at design time and made sure you had enough data so that even with this Bonferroni thing happening, you would be able to find interesting effects with this thing, this multiplier that's so much bigger. That's not a very good response to the problem for the reasons I just gave. I want to be able at design time to have control over an appropriate balance between false positives and false negatives, just like we talked about earlier today about finding something that might turn into be the next wonder drug and not finding it. And of course, fear of false positives makes your intervals widen, and fear in the other direction of false negatives makes your intervals narrow. And so think about doing this in 2 stages. First, actually 3 stages. First, you calculate your intervals with no multiple comparisons adjustment at all. You forget that Bonferroni even existed. Then someone says to you, oh, you should worry about false positives. And so you take the intervals that have no adjustment made to them and you make them what? To adjust for false positive mistakes. Wider or narrower? Wider. And now someone else comes in and says, but you ought to worry about false negatives also. And so now you take the intervals that got wider by being worried about false positives and you make them narrower. And in fact, it's possible to write out a decision theoretic approach to this problem in which you do weigh the false positives against the false negatives. And what one of my students and I have shown is that in settings where those 2 mistakes have approximately the same real-world consequences, then what you ought to do is to start with the original intervals, widen them to be worried about false positives, narrow them to be worried about false negatives, and you get back where you started, at least approximately. And so my advice from a Bayesian decision theory point of view is that if you like to report Bonferroni because you and other people are really worried about the false positives and you don't care about the false negatives, by all means go ahead and report it. But I think what we should do is we should report both that and the unadjusted answer, which is approximately the right answer if we balance false positives against false negatives. So in my opinion, we should report both pairwise intervals unadjusted and adjusted for multiple comparisons, and then explain to the readers of our analyses that the former, the unadjusted story, strikes a reasonable approximate balance between false positive and false negative error rates, and the latter concentrates only on controlling the false positives. So that's my story on multiple comparisons. It's good to know about something like Bonferroni, And there are much better methods available now. You can read about it, including Bayesian methods that are better for false discovery rate, where they only worry about false positives. Then you ought to be worried about false negatives as well in an appropriate balance against the false positives. To do it right, you have to write out a fairly complicated decision theory problem. This is actually not just a master's project for one of my students, but a PhD project. This is a serious undertaking, and we haven't got ready yet to the point where we can publish. But the basic idea is balance the false negatives against the false positives using a utility function, maximize expected utility, and what you'll find is that they get wider when you're worried about one mistake. They get narrower when you're worried about the other one. And when they balance out, you get back to where you started, so report them both. That's my story. Another topic that people wanted to know more about was something I referred to as hierarchical regression. The idea some time ago was that we would fit the standard regression model, y equals x beta plus e, where the e's are normal with mean 0 and variance sigma squared e. And then as a way of avoiding that funny thing that people do in Bayesian model averaging, where they fit a bunch of models where each x is either all the way in the model or all the way out of the model, you can create a model that captures your uncertainty about the beta vector continuously and yet does something that's something like having each variable be part way in the model by now writing a second regression. So now we take the betas and regress them on a matrix Z. So the top layer, y equals x beta plus e, the bottom layer, beta equals z gamma plus epsilon, and then you put priors on the gamma vector and on the variances. Now, to make this sensible, you need to standardize all the x columns to have mean 0 and SD1 beforehand so that the betas are all on the same scale. And the idea of the Z matrix is it's a place where you can incorporate your external information about which of the x variables should, on scientific grounds, have either large positive, medium positive, small negative, medium negative, or large negative effects on the outcome. And so basically what you're doing is, having standardized the betas so they're all on the same scale, you create a series of 6 little exchangeability groups across the beta coefficients, and you shrink them all toward the middle across all the betas that are supposed to be similar according to what the science of the problem tells you. And it's a good way to deal with this problem. There's a nice paper by Sander Greenland, a prominent, a prominent epidemiologist, and some other people in the journal Epidemiology some years ago about how to do this. And there's a paper that Jennifer Hoting and some people from Washington wrote a few years ago on Bayesian model averaging, and I wrote a comment on it, and I show in that comment how to do this as well. And the thing that I like about this is it allows you to model your uncertainty about beta continuously rather than with those silly discontinuous priors that have a point mass at 0 and then spread the mass out beyond that, as I showed you in the Bayesian model averaging approach that some people use. Some people wanted to know a little bit about particle filters, and the best thing I can offer you on that score is just what you would have done for yourself, except I can give you a little bit of perspective here. So if we go to your favorite browser and type in particle filter tutorial, you will get to this one here. This guy Arnaud Doucet is a world expert in particle filtering, and I don't know the guy from Warwick, but this is something that's worth having, and by Sunday or Monday I will have downloaded this and put it on the web page for you. What particle filters do is they work with what are called state space models, and again, we didn't have time to talk about time series, but there are a variety of ways to fit time series models, and one of them is to pretend that the stochastic process that you're monitoring is at any one time in one or another of a number of hidden states that it could have been in, and along with everything else in the model, you try to estimate what state the time series is in now and where it seems to be trending. Where is it moving? Does it seem to be moving from state 3 to state 6? You have to define the states yourself, and then hidden Markov models and other models that involve state space, unobserved state spaces, are a leading way to try to deal with data that unfolds in time in this fashion. You can also do it for data that unfolds in space and data that unfolds in space and time. And so this is a leading method for doing approximate MCMC in a fast way with large data sets when you're trying to fit models of this kind. And so this tutorial is probably well worth reading, and I think you know enough, you may well know enough to be able to stagger your way through it based on what we've covered in here so far. Then the other things that people wanted to talk about, one of them was sample size determination, and then another one was a few more ideas about approximate Bayesian calculations in large data sets. So I'll say a word about sample size determination here, and then I'll try to put more on the web page after the course is over. So this is a little bit about, I guess I'm up to number 5 in the header called Pointers to Other Topics. Five, sample size determination. Well, in the simplest setting, let's say, your model for the data is our old friend. Oh, thanks. Yeah. In the simplest setting, our model for the data is our old friend yi given mu, I the normal mu sigma squared, where we're pretending sigma squared is known, and mu has a prior, let's say diffuse, as I runs from 1 to n. And now you haven't seen any data yet, and you're wondering how big n should be. You're sitting around at design time and wondering how big n should be. And once you can figure out how to solve this problem, then ideas like it will generalize to much more complicated settings. So what do we do now? Well, we can think about what the posterior distribution is going to look like when we're done. So what is it going to look like? The posterior for mu, given the data vector y and the background information. So little y is just the vector y1 out to yn as usual. And you guys can tell me, based upon the course, what's it going to look like? Will it have a normal shape? It sure will, especially if I make the conjugate prior here is a normal centered at some number mu0, but with a huge variance. That would be a way to make it diffuse. Then this always comes out normal. And it's going to be centered where? As long as the prior doesn't matter very much, it's going to be centered where? What's your best guess for mu in this model? Y bar. So it'll be centered at y bar. And what posterior standard deviation will it have? Same answer as with the frequentist. So what do you get? Sigma over square root of n. Now, suppose you wanted to show that mu was quite likely different from some number. So let's put a value out here, and let's call it mu0. Suppose you wanted to show that. Then how would you personally demonstrate, if this was the posterior distribution, how would you demonstrate that mu0 is an implausible value based on this posterior? You could work out the posterior probability that mu is less than or equal to mu0 and show people that that's a small number. But no one asked you whether mu was less than or equal to mu0. They asked you whether mu was around mu0. And so you could ask them in return, well, what do you mean by around mu0? And they might say, well, mu0 plus or minus a little interval. Mu0, maybe mu0 plus eta down to mu0 minus eta. And now we're really cooking because we can work out the posterior probability that mu would be in that interval. And we could ask ahead of time the person we're working with, how small does that number have to be in order for you to be convinced that mu is around mu0, which is some number quite different from whatever someone else has as a theory for it. And now we just have to make a little calculation. What is that probability of lying in that interval? And the answer is going to depend on n. Everything else is going to drop away, and we have a little equation we can solve for n. Another thing you could do would be to build the 95% posterior interval for mu. And what does it look like? It's centered at y bar, and it goes how far either way? 1.96 sigma over the square root of n. And so now I can go ahead and draw. Where did the rest of the, oh, here it is. So let's go ahead and draw that little interval. So it's centered at y bar. It goes down to this place called y bar minus 1.96 sigma over the square root of n, and up to this place called y bar plus 1.96 sigma over square root of n. And now, if you wanted to demonstrate to someone that mu 0 was not a plausible value based on the data, you would want to pick the interval to be narrow enough so that mu 0 would fall outside of it. And let's call this your, as we know, this is your 95% posterior interval. Runs from there to there. And so to make it as tight as possible, we could imagine that mu 0 was right there at the edge. And now look, we have a little equation we can solve for n to work out how much data you need. Basically, this distance here is a place called y bar minus 1.96 sigma over the square root of n, but it's also called the place mu 0. And the distance there, 1.96 sigma over the square root of n, is equal to how far mu 0 is from y bar. And then the comparison, the y bars cancel. You have a little equation you can solve for n. In this particular model, I was pretending unrealistically that sigma was known. If sigma is not known, then in order to make a calculation like this, you're going to have to make an estimate of it based upon external information. Yeah, that's right. So you have to say to yourself, I think that sigma is around blah, blah, and then you can do a sensitivity analysis. You can say, I'm expecting in this experiment that I'll find out that sigma is between 7 and 10, let's say. And so now you can tell me which of those intervals, which of the places in that interval would make it the hardest to find out what mu really is, if sigma were 7 or if it were 10 or in between. Which one makes it the hardest? Sigma equals 10, right? The biggest amount of noise. And so now you make the calculation with sigma equals 10. You don't have to do the other ones. That's right. And in fact, a more careful way to do it has to involve decision theory in which you think about the real-world consequences of getting the story wrong in the two different ways that it could be gotten wrong. So careful approach would involve Bayesian decision theory, in which the action space consists of different values that n could take on, the sample size, and you're trying to maximize expected utility. You would want to try to build a cost function that is reactive to the fact that there's a marginal cost for each new data value, for example, probably also a fixed cost. So there'd be a cost function in there, and there'd be a benefit part of things based upon how accurate things are, and you would weigh costs against benefits. So there is a way forward. Now, the last thing I wanted to mention a little bit about, yes, please. You don't know y bar here, but it doesn't matter, because what counts is we're going to set the distance between y bar and y bar minus 1.96 to be how far mu 0 is from the center of the interval. And so that's going to, we'll have a little equation we can solve for n. So there's a method called ABC, which stands for, I'll put it in quotes, approximate Bayesian computation. And we just had, a few weeks ago, there was a webinar about it sponsored by ISBA, right? And some of the people in the class were involved in that webinar, is that right? Were you involved, for example? Right, SPSS, right. This can sometimes be a way to do approximate Bayesian computation in a way that actually works. And sometimes this method doesn't work very well at all. And the set of problems for which it does work well versus the set of problems for which it doesn't work well has not been very clearly delineated yet for the users. Probably the guy who did the webinar a couple weeks ago was more enthusiastic about the method than I was in what I just said, because he's probably a guy who's doing research on that method. Did he actually give some proper pros and cons of ABC in that? Did you get to watch the webinar? Okay. So I can tell you the basic idea. If you're working with a model that has a relatively low number of sufficient statistics, then, of course, Bayesian computation is not difficult even with an enormous sample size, because you reduce by sufficiency from whatever sample size you have down to 3 if there's 3 parameters, 5 if there's 5 sufficient, 5 if there's 5 sufficient statistics, whatever the story is, and then you go from there. So the ABC people have tried to build on that by creating a method that does approximate Bayesian calculations in models where you don't have a low-dimensional sufficient statistic, but you can try to write down something that you hope is an approximate low-dimensional sufficient statistic. And then the quality of your approximate Bayesian calculation rises and falls with the quality of the approximate sufficient statistics that you can come up with. So if we go and type in ABC approximate Bayesian computation, and there's already a Wikipedia page about it, and there are, thanks. So, as it says here, ABC methods bypass the evaluation of the likelihood function. In other words, they're not likelihood-based at all. Instead, they are based upon assumptions that are made about which low-dimensional summaries of the high-dimensional data set form an approximate set of sufficient statistics, and then they go from there. And the person who wrote this page, I don't know who it was, says, in this way, ABC methods widen the realm of models for which statistical inference can be considered. They are mathematically well-founded, but they inevitably make assumptions and approximations whose impact needs to be carefully assessed. Furthermore, the wider application domain of ABC exacerbates the challenges of parameter estimation and model selection. And so here is a section on pitfalls and remedies. Let's look at the motivation first of all. The basic idea involves a specific kind of rejection sampling in which you have had to put forward the vector of approximate sufficient statistics, and then they allow you to work out a rejection sampler that helps you learn about which parameter values are plausible given that vector of approximate sufficient statistics. So, as they're saying here, common approach to lessen the difficulties that arise in ABC is to replace the entire data set with a set of lower dimensional summary statistics, which are selected to capture the relevant information in D, but you, the user, have to pick what that is, and if you make a bad choice, ABC will go ahead and give you answers, but it won't give you good answers. And so a lot of us in the Bayesian world are pretty suspicious of this approach because it's not ready for prime time yet for users who are not experts in the use of the approach itself. So pitfalls and remedies. As for all statistical methods, a number of assumptions and approximations are inherently required for the application of these methods. Likewise, sufficient statistics are typically not available, and instead other summary statistics are used, which introduce an additional bias due to the loss of information. And the main problem I have with this approach is that while they admit that they are introducing bias by not conditioning on the right statistics because no such statistics exist, they don't give you a built-in way to figure out how big that bias is because they're not trying to solve the real problem that you actually have. In effect, this method is actually a bit like that class of methods I mentioned briefly some weeks ago that came out of the machine learning story called variational methods. So this is another method for doing approximate Bayes in high dimensions. And it's a machine learning idea. And a guy called Interestingly enough, given we were talking about basketball earlier today, a guy called Michael Jordan is the main guy who advocates this approach. And here's what variational methods do. Here's a space of problems that can be solved quickly. Here's your problem that's not in that space. They do something like dropping a perpendicular from your problem to find the problem in this space where everything can be solved quickly. That's as close to your problem as possible. And then they make an exact, quick calculation on the model that is closest to yours. And that's something like what's going on over here. You don't have sufficient statistics, so you pretend that you do by using summary numbers, which are supposed to be like a low-dimensional vector of sufficient statistics, but are not. And then you get an answer based upon those summaries, which is the best possible answer based on those summaries, but no idea of how far that is from the real answer that you should have gotten. And that's the problem with the variational methods. They give you a very fast and accurate answer to a problem that is different from the one you started with. They guarantee you that the problem that they worked on is the closest one to your problem in the class of problems they know how to solve quickly, but they don't tell you how big that distance is, and they have no way to compute it. So what you'd get in the end is a very fast answer to the wrong problem with a hope that the wrong problem is close to your actual real problem. And I think ABC will be found in the long run to be like that as well. Well, one thing you can do is you can create worlds, as I've discussed many times so far, where you can construct a gold standard where you know what the right answer is, and then you can pretend you don't know what the right answer is and fire up these approximate methods and see how well they do at reconstructing known truth. And the problem with that, of course, is that you have to be able to compute the gold standard to know what the right answer is. And if I gave you a Bayesian nonparametric problem with a very large data set, to actually compute the right answer with your Hadoop cluster even might take 3 months to get the right answer. And so no one does those experiments because it's just too hard to know what the right answer is. So what they do is they create little toy problems where that are simple to compute the right answer in, and they show you and say, look, in this problem here, our method got an answer that's really close to the right answer. And then you say, well, that's great, but what about my problem? How do I know that my problem is just like the one you showed me? And at that point, they say, well, let's go have a beer. They don't really have anything to say. So I would say that the state of the art at the moment is that Bayesians are fumbling to find ways of doing highly accurate approximate Bayes calculations with large data sets. I'm about to introduce this bootstrap idea in a big way at a conference later this year, and I'm interested to see how much they shout at me for using a so-called frequentist technique. But actually, any method that cuts the computation time by a factor of 10 to 100 and gives a good approximation to the Bayesian nonparametric answer is a good method to me, whether it was originally motivated frequentistically or not. And besides which, I've already told you that Efron's real motivation for his confidence intervals was Bayesian. So I think the right approximate Bayesian computation method is to bootstrap. And then when you do it right, and you end up with things that are like posterior distributions, and you can go on to manipulate them as posterior distributions, just like you would as any Bayesian. But you've been able to take things in very high dimensions in terms of data and bring them down with a much faster computational technique to a small set of posterior distributions that now can be manipulated in a pure Bayesian fashion. Yes? That turns out not to provide any real advantage over the ordinary one. He was essentially trying to point out that, in effect, what he was really trying to show was that he didn't know this is what was happening. I showed you how the samples from the Dirichlet process are like a generalization of the bootstrap, where a certain proportion of the time you sample directly from the data, which is what the bootstrap does, and the other portion of the time you sample directly from the centering distribution. And so that's essentially what the Bayesian bootstrap does. It's a weighted average of draws from the data and from a centering distribution. So it's a kind of a poor man's Bayesian nonparametrics. Okay, so we are left somehow after 10 weeks with 10 minutes to wrap things up. I would like to just write down on one sheet of paper some highlights that I would hope you would take away from this. And then that's going to give us just enough time for you to be frustrated and not being able to ask all the questions you'd like to ask. I see my way clear if in the future any subset of these people or anybody else wanted to have week 11, week 12, week 13, week 14, and so on. If we want to take a break for 6 months or something like that and then come back and do this more, you guys have a fantastic foundation now, and we can start getting into some really interesting stuff if we wanted to go deeper. So there's more if you want to go further. And I'm up for trying to help you go deeper if you want. So in the world of Bayesian model specification, which is the hardest problem we talked about all 10 weeks, because you remember Richard Cox's rules say that you have to, if you want to be logically internally consistent using his method, you have to specify these 4 ingredients, right? You've got the prior distribution, you've got the sampling distribution, you've got the action space, and you've got the utility function. So that's what we've agreed to call your model. And the real trick in the Bayesian paradigm is how to create a mapping from problem space, this is your problem, to a good choice of this here. So that's the question mark. How to do this in a way that you will regard retrospectively as a good way. And so I offer for your general taking away calibration cross-validation as a good way to approach the issue of model uncertainty in a fashion that is a principled way to quantify how much uncertainty you have in the modeling process and also be able to come away with a sense of how well calibrated you are. I draw to your attention full sample log scores and also BIC as ways of doing model comparison, where the choice between them is based upon the false positive, false negative trade-off. Full sample log scores makes more, well, I'll write it more positively. This makes fewer false negatives, and the BIC story makes fewer false positives. I draw to your attention the Draper-Kern-Yaich algorithm for answering the question, could the data have come from this model? Could the data have come from model 1, question mark? I suggest that you consider using the bootstrap for approximate Bayesian nonparametric calculations in large data sets in the way I showed you here. I encourage you to think hierarchically with random effects and latent variables to try to describe unexplained heterogeneity, which means I encourage you to think about building mixture models because they turn out to be an extremely flexible class of models for capturing non-standard behavior. And I believe I've shown you at least the first pass at how to do all this stuff with R code and background that shows what it all means and so on. And those are probably the main things that I hope you can take away from this. The first few weeks, we were learning how to crawl. So we did problems. We did our very first problem. It only had one data point in it, namely that Eliza said the patient was HIV positive, and the proposition we were interested in learning about was a single true-false proposition: is the patient HIV positive or not? Then we went to a vector of outcomes that was binary with no covariance. Then we went to a vector of outcomes that was continuous on the real line with no covariance, and we started building things like normal models and T models. We also went to a vector of integers, and we looked at Poisson and mixture models involving log normal and gamma mixtures of Poissons, things of that kind. Then we started building models that had more structure to them, where we're comparing two independent samples, like in the in-home geriatric assessment example. We talked about variable selection problems, where you've got regression, multiple regression, and you have a whole bunch of predictors, and you're wondering what's the best subset of them. We talked about Bayesian model averaging, Bayesian non-parametric methods, data sets with quite complicated structures. And in the end, I think this is the principal takeaway. I'm not going to put Bayesian non-parametrics on here because I still think it's a big question mark. The code is getting to the point where people can actually download it for free from CRAN and run it. But you are asked as a user of it to specify a whole lot of things. It's like, as I said, it's like a box, a machine with a lot of dials and levers on the outside. And you yourself would need to spend a lot of time creating data sets where you knew what the right answer is, and trying lots of different combinations of the inputs to get to see finally how you would get good outputs from it. Bayesian model averaging is not, I think, used as much these days as it was 15 or 20 years ago when it was first proposed in my work and work of other people. Myself, I would find it quite plausible to use calibration cross-validation plus Bayesian model averaging, in which I'm going to average over all the models that I developed in the ensemble when I was in that process of searching. Another thing I would draw to your attention is the algorithm for model search that I showed you. That seems to me to be something that can be quite useful. We don't know how to automate all the steps in that algorithm, but that shouldn't prevent us as humans from using an algorithm like that to guide an intelligent search through model space. Does anyone have any final comments or questions they might like to use to wrap things up? Can you even recall what your world was like 10, 11 weeks ago before you started this? We've done a lot. I think we've done a lot. Has it been helpful to watch the videos afterwards to get a second crack at things, for example? Has that been somewhat helpful? Okay, good. That gives me hope that people who haven't had a chance to come here might be able to watch them as well and go back and forth between the PDFs and the handwritten notes and so on the one hand, and watching the video on the other hand, and get something out of this. Were a lot of the videos broken off at the wrong place or corrupted or anything like that? Was it mostly pretty high quality, or did you have some problems in continuity? Did it seem like there were gaps where we went away and came back at a different place, or did it seem pretty good? I remember there was one period early on where the video was pretty blurry for a while. I don't know if you remember those days. They fixed that part. But now we have a couple sessions where things were corrupted and we can't even show you what the video was until they try to solve that. So I'm hoping that that's going to work well. In any case, thank you for your patience in coming for all these weeks. It's been great working with you, and I hope to have a chance to work with you again in the future. Okay. EC Ops, we're done. Thanks very much. The ACM San Francisco chapter has kindly agreed to provide certificates to anybody who would like one. And I am available to sit up here and sign at the bottom, and then you can put your own name in. And